I'm not taking the fall for YouTube being down. That's new. Like, I factored into my analysis of when class would start that YouTube would be live, right? All right, class, please join me in saying, "What's up, YouTube?"
What's up, YouTube?
Thank you. All right. Please join me in saying, "I do it for my fans." Can I hear a like, comment, subscribe?
Like, comment, subscribe.
Do we ring the noti bell? Do we?
You do if you want them to get your videos.
Why don't you get us for creating this humiliation that will be...
I think it's far more humiliating for me than it is for you, right? So I was hanging out, as I often do, in this classroom teaching, which is my only hobby other than playing Monster Hunter Wilds, out now on PC, PlayStation 5, and Xbox 360S. Monster Hunter tweeted out something that said, "How many hours did you play Monster Hunter this weekend?" And I looked it up, and the answer was 24. I was playing it more than 50% of the time. So this means that my lecture prep is exactly 24 hours behind, because I do nothing except work and play Monster Hunter Wilds. Anyways, shortly before Monster Hunter Wilds came out, I was teaching another class in this classroom, my other hobby. And the students in there told me that I should have fewer social media accounts, because one of them suggested I get a Letterboxd. Letterboxd? I don't know what Letterboxd is. Does anyone do Letterboxd? Okay, I don't know anything about Letterboxd, but I think the cinephiles do it. Does that sound right? Anyways, so one student who didn't know me that well was like, "Calvin, you should get a Letterboxd." And then 8 different people were like, "No, we need Calvin to spend less time on social media." So I would like to apologize for absolutely nothing. I'm not sorry for who I am. Today we're learning about bagging and boosting. These are the ensemble learning techniques. The last 2 lectures, maybe 3, are actually synthetic lectures from me rearranging things that I thought the order didn't make sense to me, so I decided to not teach them in an order that didn't make sense to me. This meant there were some, I don't know, it could have been obvious to you at 1 or 2 points in time that things were going slightly out of order, for which I apologize. After this lecture, we're back on rails until we get to deep learning. And the deep learning stuff is totally nonlinear. So deep learning was added to the curriculum for the first time last year while this was a Python curriculum. So there is no plan for how to go from where we are to deep learning in 4 weeks. We are just going to do it, and it's going to work great. Agenda, course announcements. Let's see what the course announcements are. There is a midterm coming up. It is on 3/17. It is not literally on 3/17. It is virtually on 3/17, as we discussed. These are the things that are going to be on the midterm. I have shown you this many times now. There was, Elastic Net. Today. We're doing Elastic Net today. I'm not going to ask you about Elastic Net, but it is conceptually related to logistic regression. Okay. The practice midterm is out. Have any of you looked at the practice midterm? We have time to look at it in class next time. And I'm not asking about tidy text, but an astute learner will want to use tidy text because it is the correct way to solve this problem. But it is not massively more correct. Oh, I did not update this slide. The modality. Electronic release, 6 p.m. On the 17th. And then due Friday at 10 p.m. on the 21st. So I am still preserving the 6 to 10 p.m. chunk, but I am allowing you to use any one of the days. If I give you over the weekend, you're just going to work on it on the weekend, right? You don't want to do that, right? You want to work on it until 10 p.m. on Friday. Okay, that's what I thought. The first model is due 3:10. Have you all been able to meet successfully with your groups? Is there any group problems that I need to solve? Don't say anything out loud right now. This is the indication that you should send me an email if there's been a disaster of some sort. Let me remark on this a little bit. I participated in many group projects as a student, and I was told, Calvin, when you grow up, you'll have to work in groups to be effective. And then I became a professor and used a combination of things that have been described as being abrasive and generally off-putting, and everyone loves me without exception, and I never have to work in groups. So your options are to either become like me and be generally abrasive vaguely abrasive and generally off-putting. I have the quotes. I have a little folder of things people have said about me. So I'm assuming you don't want to be like me, right? And so your options are become like me or do a good job working together with your group, right? And so why do I say this? I think it is commonly not the case where a professor assigns a project and says, one of the core learning objectives of this project is that you actually have to talk to other humans about things that happened in this class, right? That is fine. And I have given you an out. I have allowed you to do this individually if you wish, and I expect you to go sicko mode if you're doing that and like absolutely crank, right? Like I better see impressive solo projects, right? But if you are in a group, which you have opted into, right, that means that I had your informed and enthusiastic consent to be in a group, and you should take advantage of that and achieve those learning objectives, right? If there is group drama, I will deal with it, but we are all adults here, so there will not be any group drama, except like the cool, fun kind. Like perhaps a group will do like a Socratic dialogue or something of this nature, right? That would be dramatic, right? I don't remember what Socrates did, but I'm sure it was useful. Each group should create an annotated Markdown file. When I download and run the Markdown file, it should create the exact RDS or other database file that you submit. And this database file, RDS, does RDS stand for our database? What does it stand for?
Our data set, maybe?
We like data set? Yeah, okay. Whatever RDS stands for. It is a data frame, right? I will load it in as a single data frame. That data frame, which is generated by that Markdown file, should contain exactly the features that you want to be modeled by either KNN or Naive Bayes. And this thing has to be on GitHub. I am no longer accepting non-GitHub things. I don't think it is within your interests to not force you to learn GitHub at this time, so I am forcing you to learn GitHub at this time. I thought about this a great deal. I was like, am I just being like a pedantic computer science professor? And then I decided, no, I have your best interests at heart, and you can believe me or not. The modeling project is to use KNN or Naive Bayes to classify provinces. I was going to specify this. This is more so for the sake of you all being aware of technologies. I have tried to preserve the option for you all to do this in R or Python. There are, in fact, 2 other languages I should accept, and I am not providing instruction in them. I should also accept Julia, which is a 12-year-old language for scientific machine learning. I suspect it is quite bad at this because this is not science. And then I should also accept Observable. And Observable is the JavaScript interactive library that is used mostly, I think, like to make dashboards. I don't associate it as a machine learning library, but it interfaces quite well with TensorFlow, which is a deep learning framework, right? So if someone, asks you like, hey, are there any languages other than R and Python you've heard of? There's 2. You can now answer honestly, and you can say, I don't use those because they don't have caret or scikit in them. And that is a completely reasonable way to answer that question. I did a lot of interviews for, at the time, software engineering jobs in 2015. And I didn't know Java, and I still don't, and I'm very proud of that. And a lot of people ask me, oh, well, you don't have to know Java, but you have to know how to program. Like, what other language do you know, and why do you know that language, right? I think you are always better off being able to defend your language and being aware of a few of the other languages that someone could expect you to learn. And my expectation is R, Python are very big, right? But There's a good bit of C++ and a good bit of JavaScript around as well. Those are the other languages you should expect to encounter. If you go to get a PhD, you will use Julia, I think. Okay. This is leading up to the final exam. By the time you make the final exam, I feel very good that I've given you a large number of examples. Why did I go to Twitter? A large number of examples of presentations that are embedded within a browser, that are hosted on GitHub, where the source code is visible to you, where you are aware of the tools that can take the Quarto Markdown document and formulate the slideshow. Now, I don't know that you got all of your slideshows working exactly as well as mine, and I think this is too early in the semester for you to feel extremely confident about that necessarily. The wow factor on having this web-hosted stuff, my impression is quite high. People have gotten things done by being able to navigate to a website on their phone. I gave a blockchain talk off of my cell phone once because I had to give a lightning talk somewhere. When people see that, they get impressed. I want you to have that power. That is not the point of this class, but the point of this class is to end with a presentation, right? That is within the enumerated learning objectives. My claim is that in 2025, for people in computational disciplines, this is the way to give presentations. There is no competing technology. The closest thing is LaTeX PDF, and I'm not going to teach you LaTeX and PDF, so I'm going to teach you Quarto. We are not linking up to discuss the model and the homework today until after lecture, so I'm letting you know that. Okay. At this time, I have to do 2 digressions, and these digressions are both related to some of the other things I saw previously. So I have detected 2 patterns on submitted homeworks that I would like to address to the class as a whole, because I think it is of benefit to all of you. These are things that I do consider mistakes that I did not respond to as individual feedback because I perceive them as systems level errors, and so I'm going to attempt to address them for all of you. The first thing is having a sense of what I call state. And so I'm going to try and open VS Code and live code in front of you and see if I can actually solve this problem and motivate the solution. You should be able to follow along in RStudio or VS Code. I actually don't know why RStudio stopped working on my computer, and because the battery died, I didn't have time to fix it. So this could have been done in RStudio. I don't think it matters. I'm going to make a new thing. Don't save. And I'm going to save this as Quarto Markdown. And where should I put this? I'm going to put it in my Documents folder. I'm going to make a new folder. Oh, WITS has approved my request to buy a new laptop, so at some point in time, my laptop will just suddenly start working in class, and will all be very exciting. But look at this. I don't know what it's doing down there, but it's been doing it for a long time. As I'm creating this new folder, I want to narrate something. Less so in this class than in classes in general. I have perceived a decrease over time in familiarity with what I call the file system with students. And I think there is one specific core learning objective that is being lost, and that is the notion of paths. There are 2 forms of paths that describe the relationships of files to each other, and they are highly relevant to you when you read in the wine.rds file. So let's look at this. I want to, okay, this is in class. Let's save. Okay. I have successfully saved something called untitled1.txt in my in-class 3, which is today. I don't actually want a .text file, so I'm going to see if I can rename this. Can I do that? Does not look like it. We'll make a new file, and I'm going to call this inclass33.qmd. Okay. I'm going to name it .qmd.qmd, which is not at all confusing. So whenever I start working with a Quarto Markdown document, I like to start with a reference document. In the case of this class, I often use all of these things that are provided here. And my favorite one to begin with, I'm just going to use KNN. Why am I using KNN? KNN has training in it, and oh, my words are not working today. I had my first coffee at like 5:47 today, and it was very weak coffee. I don't know if that affects you at all, but that's something I thought about. So here is example of a Quarto Markdown document I have provided to you that you can begin working with, right? I'm just going to grab some of this stuff. Let's see, I'm going to want to get the pno.rds. I'm going to specify that I am Calvin, and I'm going to update the date. I'm going to, at this time, get something minimal working. And the minimal thing that I'm going to get working is that I am going to run tidyverse, or I'm going to import tidyverse. I'm going to read in a data frame. I'm going to do all of this in VS Code, so you should be following along in VS Code if you haven't done this before. And then I'm just going to look at the data frame quickly. Or I should say headwine probably. Is this how you, in data 501, how would you view a data frame? Would you do something like this? Is that reasonable? Okay. Let's see. Yep, I pressed some buttons and I don't know what they were. I'm going to run this, and it is in fact going to take a moment. I don't know how long it takes to... I'm accustomed to this process being called knitting PDFs, because that's how it was commonly called in RStudio, right? We are not necessarily working with PDFs anymore. We're working with different technologies over time, and that is okay. As this is running, I can go back to the folder I created and see what's going on there. Perhaps I can, in class. This folder here, I created in class 3.3. I did not create .qmd_ files. That is being created by the Quarto process. And so there's a bunch of stuff going on in here. And I don't know what all this stuff is, and I don't think you do either. And we want to be cognizant of the fact that when we do something like knit a document, create a ggplot, download an RDS file, stuff is going to happen. And we don't necessarily know what all of that stuff is. This stuff that happens is a useful framework to think about not just running R language scripts, but it is also a useful framework to think about to doing things to R data frames inside R. And I'm going to think of them conceptually the same way. Has this successfully run yet? Okay, so let's take a look at this. This is something I got working relatively quickly, and I want to narrate a few things for you. This is a website hosted on a web server. The web server is running inside VS Code locally on my device. That's what localhost means. I am running a web server to project this. I think some of you maybe have used things like Shiny apps, right? I think this underlying technology is quite similar. To me, the benefit of relying on Quarto to do these things is that people that are paid to think about this matter have put in the effort to make this look professional and nice and well done. Separately from relying on the web server, I have also created an HTML document or file. This HTML document or file is called .qmd, and it's right here. Whatever's going on in Quarto, it's serving a web server, but the only thing that web server is doing is it is giving me this document. So I can also open this document, and I can see that I see the same content. I'm being served the same content, but this is looking at a location on my file system, and this is looking at a location on the internet, right? Both of these things correspond to actual locations on my device. They correspond to bits that live on my solid-state hard drive, but I can do some different things with them. One of the things that I can do differently with this .qmd file is I can turn it in. So I can take this .qmd file and I can email it to my favorite professor, or also the professor of this class, who may or may not be the same person, right? I'm going to treat that as storing something inside my downloads folder. Can I make this larger? Can you see that okay? I don't have any idea what's in my downloads folder, but you can see I was doing something in C++. I can once again open this, and we can see that in addition to having a documents in class 33.qmd.html, I also have a downloads.qmd.html. This all still looks the same, but I want to point out something very sneaky happened. When I copy-pasted .qmd from in class, I did not grab .qmd files. That came on its own. And that is relevant to me because when you email .qmd to me, not in every case did I always get a .qmd files folder as well, which perhaps would be encoded as a zip or something. Let's see. I think I can delete that, and I think I deleted that successfully. Is that true? Oh, did I deleted everything? How sad. Is this gone? I pressed some keys and I don't know what they were. There it is. Okay, .qmd. I believe I can delete just this folder. Oh, did that delete everything? Within the Windows file system, and I'm working on Windows, I don't know what happens on Mac. Quarto or RStudio or Posit Cloud or someone has somehow linked this .qmd.html file to the .qmd folder. That's weird to me. And so, let's see, can I make a copy? I'm going to try and copy this. Can I? Let's see. What happens if I rename it? If you rename this file, it will no longer belong to the folder .qmd files. Okay. I can open this and it still works, and then now can I delete this? This process of changing the name of a file causes it to no longer correspond to the same other files within my system that could include, for example, styling elements, or most prominently, some of you have had the disappearing plot problem. You turn in an HTML document and none of the plots show up. I think if I come back over here, we can probably get some of this stuff to disappear. And let's see what's going on here. All of these .qmd files are now referring to places that do not exist. Let's see if I can open this with Chrome. This may look familiar to some of you, and this is an example of a Quarto Markdown document that is not styled correctly. And let's put them side by side so we can see what we're looking at. Okay, here we go. So what are some differences? To me, the one on the right looks professional and well done, and the one on the left doesn't. It looks unfinished, it looks unpolished. I really particularly hate this thing here. I don't know what that is, but that clearly corresponds to the box that's supposed to be around here, and probably this little button right here, right? a certain number of the HTML files that have been saved on GitHub, when I download them and look at them on my computer, they look like this. If I go through a more extensive process, I can demonstrate, I can put in a plot here. What should we graph? Make a graph. Oh, A should be lowercase, right, because it's a title. Oh, my computer is struggling. ggplot is included in tidyverse, right, so I don't have to re-include it? Oh my gosh. Ah! Is that right? That looks wrong to me.
No.
It's percent, right? Oh my gosh. Yeah. No, I pressed it again. Okay, percent. There you go. What should I do? Oh, you do the plus on this line. Okay. Geom. Is that right? How do I do ggplots? Geom underscore line. If I do this, will it give me something? I probably have to do. Is the AES in here? What did we do? We did points versus price, right? Is this right? Does anyone know how ggplots works?
No.
Is that right? I'm going to run the cell. Let's see if that works. Run the cell. Oh, it goes up here. I see. I know how. Oh, is this actually? Okay, apparently you can put it wherever you want.
Yeah, you can put it in either.
Well, now I have to try it because I'm not sure I believe you. I do want to point out I'm showing off one additional feature of VS Code at this time. You can pop up plots here. I think you can do that in RStudio too. I don't think that's too exciting. But I don't know how many of you have played around with running cells, right? So I can run this cell again. And I get the same graph. So maybe this is not a particularly good graph, but it's enough for our devices. So let's go ahead and re-render. And I do want to point out, I don't know if I can get clicked over to it in time. Where is it? See, this is showing me that it's updating it on the server, right? And that's kind of cool. Okay, I think we're all set. Is it all set? It seems to be struggling. How long does it take your computers to render a ggplot? This is slow. Oh, well, okay, it's here. Ta-da! I'm making this big so you can see my tabs again. Of note, this one, which is the file is static. When my web browser rendered this file, it does not keep going back to the file to see what it looks like. It created a visual representation of the file. It has embedded text, right? This is no longer what this file looks like, but it is still displaying this way in the browser. Oftentimes, I'm used to seeing this. I've heard I spend too much time on social media. You know how always right before you refresh a page, you see like a really cool post you want to interact with, and then you can never find it again? That's what's going on here. If I refresh this, then I get the graph. I refreshed it with F5, right? That's this button here. This file no longer exists. That's okay. Let's go back and grab it again. I was in Documents. I was in class 3.3. I would like to emphasize at this point in time, I am remembering which folder I saved files in, and I am remembering how to get to them. I have not necessarily had a problem with you all doing all of this, but a very large number of times I've asked students, where did you download the file? And they say, what do you mean where? So I am belaboring the point that there is a file system with locations. Have you seen this in the Quad Center, Kendall?
Not in the Quad Center, but in 151.
In 151, our most beloved undergraduate class. We can do the same thing here. I'm able to open .qmd. I'm able to rename this to .qmd3. This breaks a linkage. This is very weird. I actually do not like that this is possible on a computer. It makes me uncomfortable. We can open, oh, I'm trying to take a screenshot. And we have the same problem. And notice the graph is gone. This is the case of the mysterious missing graph. This is what causes it to disappear. Do not allow your graphs to disappear. There are a few ways to fix this. One of the ways is if you're using GitHub to also upload that entire .qmd files folder. And I'm going to show you another way right now. You may remember I spent a great deal of time talking about embed resources. We're going to embed our resources, and we are going to re-render the website, and we're going to talk about our day while that's going on, because we have a lot of things going on. So how about, are there any sports leagues going on right now? Which ones? You nodded. What's happening? Baseball. How about them Yankees? I know who the Yankees are. Cubs? Sox? Yeah. Bears, Cubs, Sox, Bulls. A lot of statisticians, I guess, honestly got into statistics because they spent a little bit too much time thinking about how fun it is looking at the baseball numbers. We love Moneyball, right? Because we love money and we love to ball. Yeah, that's two good things, right? Okay. Let's make another folder. I'm going to open two things in my File Explorer, and I'm going to do this for a reason. Gosh, I wish there were a better way to do this. Does anyone know a way to split your screen horizontally in Windows? Let's see. Am I smart enough to do this? Let's see. Do things manually. Disgusting. Okay. Oh, I can just drag this over. Okay. We'll drag this over. Okay. What would I like to show here? I added the embed resources format specification to my Quarter Markdown document. In this class, I've already taken time out of class to go through the Quarter documentation and show that to you. I suspect a similar thing exists for RMD. There's going to be some version of it, right? And you all know how to read documentation just as well as I do, right? What is happening here? .qmd_2 is 24 kilobytes in size. We added an image to .qmd3, and it became 1 kilobyte in size larger. How big is a kilobyte? Kilo is 1,000. Byte is a byte. The thing that we classically store in a byte is a single ASCII character. This document is 1,000 characters larger than this document and ostensibly contains an image. It is unreasonable to conclude that we can specify what an image looks like in only 1,000 English characters because a picture is worth 1,000 words, and there are only 2 words that are a single character in length, plus we don't have spaces, right? So this file is much larger, much larger. This says 25 kilobytes. This says 1,155 kilobytes. That is 46 times larger, right? I can look at this, and to me, visually, it appears almost identical. There's one kind of goofy thing that's going on here, which is that this image does not live in a .qmd_ files. There is no .qmd_ files here. So where is this image on my device? It is nowhere. It is embedded in a URL. This is a very long URL. In fact, this URL is approximately 1 megabyte in length, I think. Let me show you some things that are kind of nice once you add embed resources. First of all, this file is an absolute mess to work with. It's huge. But I can drag it over here to downloads. I can change its name. Please open. It's taking time. Once I add embed resources, all of the styling, all of the font choices, all of the cute little copy-paste buttons, and in fact the image, are all included in a single file. Let me show you what this file looks like, and I'm going to open it in Notepad++ because that's what I look at my HTML documents in. There is a lot of nonsense in here, but all of these things, for any of you that do web development or have any amateur interest in that at all, these are just ways of telling text how it should be displayed in a web browser. Let's see. Can I find it? And this is the image file. This line of text encodes the description of an image, and that line is 1,181,754 characters long, that is almost exactly our file size in kilobytes. Almost the entire file represents that image data, right? I know what you're thinking. You don't believe me. You think I made that up. No problem. I'm going to delete this line, and then the image is going to go away. And there it is. It's gone. I suspect you still don't believe me. No problem. I'm going to copy-paste this line. I'm going to put it in a new file just so you can see it. I'm going to change the view. I'm going to turn off word wrap so that you can see how much text it is. This is how we specify images for some reason. I don't know. I thought this was cool. Imagine asking ChatGPT what this represents, right? And you can treat that information exactly as an image. Now, someone who really has a lot of time on their hands would think, wait, does this mean I can manually type image data into a web browser? And in fact, you can. You can just go in here and start changing some of these. And if you guess correctly, you'll still get an image you can see. All right, let's go back. Can I change this one to B? Nope, that didn't work either. How about one of these ones? We're close. Cannot be displayed because it contains errors. We tried so hard and we got so far. Yep. Okay. So with the benefit of all of that going on, I would like to apply this same idea of keeping track of where the information, because this, in fact, that image data was information, right? It had to be given meaning by us. It was not really data. We wouldn't think of it as the description of a graph. That's not how we tend to describe graphs. We should also do one other thing, which is that we should get a little bit used to keeping track of our data frames when we are doing machine learning. And I think of this quite clearly as occurring in a few steps. So the error, look out for this. The thing that I think was bothering people this week is the notion of what exactly do each of the sort of components of the machine learning workflow do, and in which order should we do them? Look out for what order we do things in. To me, machine learning proceeds in the following steps. We take a data set. Optionally, we engineer features. We split the data set. Do you do space between data and set? Is there a style guide? Okay. Into train and test. We use the train data set No, this is training. Two, and what do? We take the training data set and we use it to create a new function. That function is the predictor. So we're going to use the training data set to create a predictor. The predictor, let's see, we'll say create a predictor which takes an observation. What is an observation? It takes a row from the data set. The row doesn't have to exist in the data set. It can be any possible row in the data set. And it returns a classification. Or perhaps regresses some value, right? It predicts some value or predicts some class. So then what we do is we use the predictor to make predictions of the testing data set, and we measure the performance on the testing data set. Why do we do things in this order? Can I push this down? We do things in this order because it is a little bit too easy to change the order of engineering features to go after the train test split. When you take the engineering features and put them after the train test split, you are likely to encounter a problem where the predictor, which is expecting to see observations that are the exact same form of observations as are present in the training data set, there could be any number of differences in engineered features. I perceive the R project for statistical computation as slightly unstable with respect to this train test split. It seems like if you do the exact same feature engineering on both sides of the train test split, sometimes it doesn't like that. And I think it's doing the same hidden thing that Quarto was doing, where it's creating files on your device and you don't necessarily see them and you don't necessarily perceive them, and then R doesn't work or something, right? The other reason to do this is there is a sort of philosophical experimental design reason to do this, right? We do not want to train and test on different populations that have been treated differently, and we don't want to differentiate them in ways that are unhelpful. For example, if every single line in our training data set we have a one-word description, and every single line in the testing data set we have a multi-sentence description, that is unhelpful, right? But it is very easy to accidentally create two such data frames using tiny words, right? So, some of the errors that I think I have been seeing have come from not thinking of this in terms of sort of the experimental design of we create the data frame, and then there should be a firm separation. Then we do the machine learning process. Feature engineering should be temporally and conceptually separate from the machine learning process. We do all of the changes we are going to make to a data set before we do anything related to machine learning. Now, after we do some machine learning, we may want to go back and engineer some other features. That's completely fine. But then you have to do the whole process end to end once again. I'm going to write down a few other things about how I think of this. Think in terms of types. I think of a data frame as a list, array, vector, collection, or enumeration. So I'm going to say list of observations. How do you spell observation? Observation. Did you all use the term observation in Data 501? Is that common? I think of the tidy in tidyverse referring to giving every observation its own line in a data frame, right? An observation is a collection of measurements. Each is unique, and each has a measurement for each column. Each observation is a row. Let's see, no, not data engineering. Feature engineering is a process which takes a data frame and produces a new data frame. This data frame may have different columns or measurements, but is derived from the same underlying observations. When we engineer a feature such as this wine is from New Zealand, we are not adding new information to the data frame. We are changing the format in which the data is expressed, right? But when we change that, if we have created a predictor from the machine learning process that does not expect to see whether a wine is from New Zealand, that predictor can no longer function. Training, or the caret train function, takes a data frame and produces a function. This function takes an observation and returns a value or a classification. My typing is getting slow. Wow, it is, oh, there's, okay. When I'm typing, there's lag, so I can't see if my key's logged. It's breaking my brain. Okay. Have you ever all thought about function types ever before in your lives? Okay. I am dogmatically attached to the idea that if people are typing things into a computer, they should think about what type they are. I think this about not just programming, I also think this about Microsoft Excel. I also think this about email. I think it is good to think about who your target audience is, what the inputs to something are, and what the outputs of something will be. We can express this as follows. Training has the type data frame. Given a data frame, it produces something. What does it produce? Well, the predict function is similar to the training function in that they are both functions and they differ in types. So training takes a data frame and produces a function. That function is of type observation, arrow, classification. And we have the special caveat that the predictor, the observations in the predictor, can only work over observations of the same type as are present in the training data set. So, if you produce a training data set from the train test split and make any change to that data set, if you engineer any features over that data set, you should expect your training process to not work successfully. I perceived this to be a common error. I don't know the best way to think about it. I think about it as, in a perfect world, there would be one function, and I have in fact wrote functions very close to this in class, that takes a data frame, performs the train test split, does the training, reports the kappa value, and that's it. And you don't see any of the internals because you don't want to be messing with things during the process, right? I don't like that the caret train is different from the caret train test split. I want it to all happen at the same time. That's sort of like not how things happen in real life, right? So it makes sense that this difference is preserved. There's a very nice thing that there is a style that has come up around the scikit-learn technology where there's a strong culture of having very specific ways of naming variables at each stage of this operation. So there's a community consensus on how to prevent you from making mistakes with this. I don't know that there's a consensus around what to name your training and testing data set in R, but the thing that set off this whole talk was I realized I had a function named train, and I was calling a data frame named train, and that is really bad. That means I was very confused, right? So I'm hoping you are no longer confused, and I apologize for that. See, what is... Right. We should also specify, let's see, how do we think of e.g. kappa? Kappa takes a predictor which takes observations, I accidentally put myself in a spelling bee up here, which takes observations and returns a classification and a data frame. By convention, the testing, I'm going to lowercase t, okay, data frame, and returns a numerical score. This numerical score measures the goodness of the fit, right? I'm only specifying what this actually does, right? So we have an additional step in our process here. I did a process 5 here, so we can begin, for example, at step 6. So 6 is measure goodness of predictor by predicting every observation's classification within the testing data set comparing to the actual classification, and then repeating the process from step 1, which is getting the data frame, if necessary. When I say from step 1, what does that mean? If my machine learning process fails or produces some bad result, as a rule, I like to read from the RDS again in some way. I like to go back to ground truth and start there. I don't necessarily want some of my features that I engineered to persist around. There could be errors in them. They could be causing bugs. My thinking might have been unclear. There could be an information leak. Any of the things that can go wrong when I engineer features can show up when I calculate a kappa value, or find any other way of making an assessment of the goodness of fit, right? So when I finish the machine learning process, I start again by reloading the whole data frame. Okay. The only other thing that I would want to mention before we go this is back to the notion of files and relative types and relative paths. It was my strong recommendation to use a URL here this term. One of the reasons to do that, I did, I think, something that is relatively interesting today, which is that I saved this Quarto Markdown file, I rendered it, and then I showed I can move that Quarto Markdown file around. This Quarto Markdown file can run anywhere within my file system, and I'm going to demonstrate that to you by moving it. So let's see, this is the QMD file, and we're going to go into pictures. I have some screenshots here. Here's my Quarto Markdown file. I can open this. Yeah, open it. Why not? You'll see these are different Quarto Markdown files. I did not have to update this URL, but I can render this document the same way I rendered the other document. This is why I have recommended the use of URLs. When I ask you for a Quarto Markdown document for you to turn in, if it has the URL in it, I can run it directly on my system without having to download WineRDS or Pinot.rds. This is very cool, right? There is one combination of ways of communicating data that is extremely ineffective. if you both do not embed resources in your HTML document and do not use a URL for read RDS, it is possible that I cannot reproduce what you are using on your device. I need one of those two things, right? Your non-technical manager needs both of those two things, right? But I am your technical manager. Separately, everything that's happened that I have talked about today, I didn't have a particular hard time debugging any of this. So like no one has turned in code in this class that I could not get working in a very short period of time. This is very good because I don't know how to use R and I don't know how to use machine learning and I'm not totally sure about computers, right? So there were no problems that were that bad. Everything could be fixed relatively quickly. You all could fix every weird thing I see if you just reviewed 30 assignments every week, which is all I'm doing. That's how I know the solution. If you see something 27 times that works and 3 times that doesn't, you figure out pretty quickly what's going on, right? You don't all necessarily have the benefit of that, but this does mean we're all very close. All of these little things that are kind of annoying, you can fix. The reason I wanted to spend very close to an hour talking about this is I think there is a systematic approach to causing these problems to not exist in your life, and that systematic approach is thinking about what is the actual information in the computer, how is it linked to other information in the computer, and what steps and processes can we use to be very consistent. I did not think of this portion of the talk today necessarily as a computer science or data science talk. To me, I'm doing systems engineering right now, perhaps even human systems engineering, right? And that is the solution to these problems. Do things the exact same way every time. Do not do something if you don't know why you're doing it. Figure out why you're doing it. You can just ask me, right? But I think we had a very productive conversation earlier in the term about embed resources solving a problem for us. And it solves the problem of how do I deal with all these annoying image files that are floating around, right? You can just jam them all into a big HTML document, or you can manage the files yourself manually. I don't care what you do, but you do have to know why you're doing it, and you have to know what problems can be caused if you don't do it. How many of you love rendering to PDF so you don't have to think about all of this stuff? Boo, yeah, boo PDF, excellent, right. We're PDF haters in this class because PDF is owned by Adobe, and Adobe is not owned by Posit Cloud, and Posit Cloud is part of the Open Source Alliance, so we love and respect them. Okay, does anyone want to ask me any questions about any of this annoying stuff we went through? I'm assuming you don't actually want this card on Markdown document, but I'm going to give it to you just in case. Am I? That's a lot of work. I'm going to do something even more obnoxious. You'll love this. I'm going to put it on GitHub because everyone loves GitHub, right? Can I hear it for GitHub? That was very half-hearted, which is exactly what I was hoping for. I'm not going to create a secret gist. Ugh. Okay. And let's see. How do I share this? Does anyone know how computers work? I do. Okay. I think all of this stuff we did actually would probably more properly be considered data engineering. So, sorry. Oh, that's all secret. Don't look at that. Okay. Did you all look? I'm going to have to edit that out of the video. Do you know how much work that's going to be? Okay. Cool. I have to close approximately 1 million tabs, and then we can get back to work. I don't think this is still true anymore. There was a point in time where if you had too many tabs open in your web browser, it caused your computer to slow down. You all accustomed to that? VS Code and RStudio are both web browsers. I don't know if the degree to which you've all realized this, but I demonstrated, for example, that this is a web server, right? This is a web browser on the right-hand side of my screen here. And every time you knit an R document, that's just being hosted on a web server, and then RStudio is viewing it as a web browser. So if sometimes you feel like your computer is running slow in the same way it would if you had too many tabs open, that is in fact what is going on. The tabs are just open in RStudio and VS Code. I don't know. I think it's cool. I mean, it's not great. It's pretty annoying, but that's okay. We make lots of interesting design decisions. Cool. Weighted penalty. These are the libraries I use today. Hopefully it is obvious to you at this point in time, after seeing me attempt to type into my computer while R was running, why I'm not going to run this code live in front of you, because it would finish running about the time we get out of class, right? But I have a new laptop on the way. Okay. I think these ones are not super new. I think these ones are pretty new. The rest of this stuff should be familiar, and we're going to get to this later. I am using my URL method to reliably get RDS documents, right? I think you can do this to like Kaggle and stuff too, right? You don't have to wait for me to host an RDS on my website. And you can put your own things on GitHub as well, right? This is just a GitHub URL, nothing too exciting going on there. And I am putting IDs inside my data frame. I am doing that at the very beginning, before I do any feature engineering, before I do any train test split. This is the very first thing I'm doing. I'm going to work with a data frame that is augmented. I use the term. You can equivalently say mutated, whatever, however you want to think about this with IDs. Is this an unusual way to add IDs? I notice I'm not using a mutate there. Is that goofy? Do you hate this? How would you do this? I don't know another way to do this. I just saw it from Hendrik. This is the WineWords super function. I tried to fit it all in one line, and it was untenable. But we stepped through the process of creating this whole thing in previous classes. Hopefully it's vaguely familiar to you. You probably remember, for example, discussing the interesting things are the right join and the pivot wider. And then there's the goofy thing where it doesn't matter if you put parens on group or not, which is odd to me. This is the process that I spoke about earlier. What is going on here? I am engineering all features before I do any elements of the machine learning process. I do all elements of the feature engineering workflow. This is all of my feature engineering. I bundled it up and I put it in a function. It is this function, WineWords. I am taking words that appear at least 1,000 times, and I am using stems. Once I have engineered those features, over this data frame, and this data frame is fundamentally different from wine.rds, right? It contains the same information, but in a different orientation. Then I'm going to create a partition, and I'm going to create the train and test data frames, okay? From there, I'm going to specify this thing, and at this point in time I should reveal that I made some simplifying descriptions of the machine learning workflow. I claimed earlier, as a simplification, this is not false but it is incomplete, that train takes a data frame and produces a predictor. That is underspecified. It takes many more things than that. It takes one of these things, which can be called a formula or perhaps a distribution, a way of specifying that which we are trying to predict. It takes the training data set. So I have to provide some data set, and by convention this is the training data set. It has this train control thing which specifies some of the manners in which the machine learning process is being conducted. So this is what I am predicting in line 1, over what I am predicting in line 2, the manner in which I am constructing my predictor in line 3. Line 4 is the method. This is how the predictor will function. So a multinomial prediction will take a variety of observations and predict one of many possible output classifications. And then I have a maximum iteration. This is how much money I spend on my process, right? So what I am trying to predict, what I am using to predict it, the manner in which I am developing the predictions, the mechanism through which I am making a prediction, and how long or how hard I'm going to try, right? And you've seen all of this before. This is nothing too exciting here, right? I claimed that train produces a predictor, and this predictor here is called fit, right? How can I use this predictor? Well, one way to do this is to apply the fit to all of the testing data set. So I want to be clear here. I claimed the predictors that we produce, or the fits we produce, they take as input one observation, one row of the data frame. I am not doing that here. I am providing an entire data frame. What is happening? Well, this predict operation is simply taking the fit and predicting every single observation in the incoming data frame. So I'm still using a predictor. It is still just taking observations, and it could predict over any number of observations, right? I could put in made-up observations that don't exist, but they would all have to be the same size and shape and area and whatever. They would have to be compatible with the data frame over which I trained. This creates my predictor, and then using the predictor, I'm able to generate a confusion matrix. And I think of this as similar to calculating kappa. And in fact, I probably have a kappa value here, right? And it is pretty good, right? I have all these statistics and so on, right? So the end-to-end process: load in a data frame, engineer features, train, test, split, train, predict, and assess, right? All of these processes, and there are reasons for them to proceed in that order. Like, each one of them necessarily follows the other one. We cannot assess our predictor before we train it. We cannot train before we do our train, test, split. We cannot do our train, test, split before we feature engineer, and so on. Now, one of the problems with this is that it's not particularly good at predicting Marlboro wines. It's not particularly good at predicting New York wines, and it's not particularly good at predicting Casablanca wines. In fact, it is atrocious at predicting things that are in the Casablanca Valley. And where is the Casablanca Valley? Yeah, Chile, right? Where's Marlborough? New Zealand. And New Zealand has a different name now. Does anyone know its new name? It begins with, do you know?
Like the actual name?
Yeah, they changed the name of the country to the Maori name.
Like officially, or like we changed it?
In my heart, it's Aotearoa, but did they actually change it?
I thought I read on the internet they changed it, which means it happened.
I would be surprised. But
This is what I was trying to remember.
Aotearoa.
Aotearoa? Sorry.
Aotearoa.
Aotearoa. Ah! Oh my gosh. It's bad enough when I have to say words that I know. Say it again. Do you know?
Aotearoa.
Aotearoa. Ah.
Aotearoa.
Aotearoa. Roa. Oh, Roa?
Roa.
Roa. Okay.
It's like
Aotearoa. Okay. I feel good about that. I don't think I'm doing a good job, but it's important that I feel good, right?
You tried.
Did I? Okay. I think I could have tried a lot more, is what I'm going to say. I don't know why I'm picking on New Zealand. I don't know the actual name of California. It's presumably not named after the Eagles song. Any boomers? Yeah, okay, right. Okay, so it's important to remember Aotearoa. Oh my gosh. Because, you know, all elements of our data set are worthy of respect and consideration. Do you remember when I played Weather Girls, It's Raining Men on the first day of class, right? We want to remember everyone, right? We have a responsibility to do that as data scientists, right? And so if we're doing a terrible job predicting that wines are from Chile or Aotearoa, or wherever New York is, which is on Iroquois land, but the Iroquois go by a different name as well. Burgundy is in fact in France, right? So all of these lands matter All of them are important to the people that live there, right? They're culturally significant, so we have a responsibility to pay them equal weight. Now, one of the problems, as you all probably know, being people that live in Oregon, is there's a bunch of Californians that keep coming up here and ruining things, right? I think we're all familiar with this, right? So some of you may know, for example, my good colleague, Professor Heather Katada Smalley, right? It's a Californian coming to Oregon and taking our jobs, right? That's someone who's gainfully employed in the state of Oregon, right? And I'm from, where am I from? I'm from either Colorado, Illinois, or North Carolina. Yeah, just decide who you don't like, right? And so we don't necessarily just want to only predict things based on California. Now, there's no reason to necessarily assume that dramatically more wines do or don't come from California, or that dramatically fewer wines do or don't come from the Casablanca Valley, right? The only thing we know is in our data set this happened, right? California is geographically larger than these other regions, right? But this could be something caused by, for example, Californians having a lot of money and therefore employing more wine tasters, right? We don't actually know what's going on. So one of the ways to address this problem is that we can create some weights. Who in here loves progressive overload, right? Okay, yeah, progressive overload. My partner has this app called Stronger by the Day, and every other day comes home from work and tells me what her deadlift training max is. And I have to remember it, so I know what the delta is, right? I use like 85% of my cognition remembering my partner's deadlift training max, right? And you should do this too, but not with your partner, with this class. And you should remember the training weights for Pinots. So here is a naive way to do this. I'm going to say that if something is from California, it is worth 5% as much as anything else, right? This is what I would do with property values if I could, and then we could all afford to live there, right? So what is going on here? I am engineering a feature, and I am creating something called weights, and it simply checks to see if the province is California, and it gives a weight of 1 if it is, because boo California, right? Is there anything good from California? Smalley, yes. I was gonna go with like the Oakland Raiders. Are they good? Wait, no, that's the wrong season. Wait, what?
They're in Vegas now.
They're in Vegas now? Vegas is taking Californian jobs? Is there a baseball team in California? Maybe the A's? Are the A's still in Oakland?
No, the A's are in Vegas.
Is there anything that's not in Vegas? Is Deadmau5 still in Vegas? Okay. All right. Sorry, we got to get back on track. Oh wait, no. I have to be okay. What did I just say at the beginning of class? Under absolutely no circumstances should you ever be engineering features on the training split of your train test split. And so what did I do on this slide? I engineered a feature just on the training data of my train test split. Why did I do this? This is not actually feature engineering. This is part of the machine learning process, right? This is a hack to specify something within the training function. The same way I specify the control, the same way I specify the method, the same way I specify the maximum iterations, I can also specify weights. And the manner in which I have to specify weights, to the best of my knowledge, this is the only way I got it to work, I can't just provide this function, which is what I want to do. I want to say if else province equals California 120, right? That's what I want to say. It seems like R has a strong preference for this being specified as a data frame that contains the weight for each observation. Obviously, there's good reasons for this, right? We might want to manually set weights for some observations. That's totally fine, right? I found it a bit confusing, and I've tried to specify this as closely as possible by creating a data frame that is identical to the train data frame, except it additionally contains this weights column. And then I train over the same training data frame, and I provide the weight train weights as the weights. I tried to be relatively disciplined about referring to everything here. Here's some problems that you might experience by accident. If you just throw weights directly in training, then the model will also attempt to predict things based on the weights. That's weird. You don't want to like find out that wine scores are positively correlated with having a high weight in your model. That's weird, right? And that's why it's different than feature engineering. So this is my recommended way to add weights to models. This is the last really cool and also relatively basic thing that I think we've done with classifications, and so I wanted to introduce it now. This helped a little bit, but it really results in California wines having a bit of an identity crisis, right? You'll notice we have extremely crisp Burgundy prediction. We're pretty good on the Casablanca Valley. No one can still tell Marlborough from Oregon. Perhaps they're the same place. New York got something. That doesn't look healthy, right? And Oregon's doing much better, right? So at the expense of accurately predicting New York and California, we got much better predictions in our other categories. So, for example, if you were the city of Las Vegas and you have apparently some beef with Northern California, right, this might be your preferred way to handle weights, right? Which is odd because Las Vegas is like not part of California on a technicality, right? Like, take a look at these weights and think about them for a moment. My hope is that you will have some rapid intuitive sense of from where they are derived. We give Burgundy a weight of 3. We give California a weight of 1. We give the Casablanca Valley a weight of 37, the same as New York. We give Oregon a relatively small weight, 1.7, and Marlborough 18.5, just about in between Casablanca and New York, right? Do you all see where these weights are coming from? Do you perceive it? If I take how many wines are from Burgundy and multiply it by 3, it is equal to the number of wines from California times 1. Here's one way to train. You see I'm training with my weights. My training max is going up. Follow Meg Squats on Instagram. I hear a lot about Meg Squats in my life. This is perhaps a little bit better, but mostly what's happening here is we now have the biggest bin is the accurate bin in each of these. And you'll see we have correspondingly lower performance in California. Some of you at this time will say, wow, I should do a decision tree and split out all the California wines somehow. And you remember, we could do this relatively easily with like black cherry fruit tannin or something, right? So these weights should be a component of a broader, healthier model. In fact, our kappa is going down when we wait for this because we have such a California slanted model. And that way, it's much like the United States House of Representatives. Okay, moving on. I'm not going to ask if I can hear it from the United States House of Representatives. I'm not going to do that. Okay. This is how I generated this. And I think that's really cool. And your job is to do this exercise. And we're going to do this for 9 minutes, and then we're going to go to dinner. And we're probably going to work on it a little bit when we get back, because 9 minutes is not enough time to do this. A fun thing to do. Take the Pinot data frame, take out California. It'll be much faster. Try and find weights without California. Ready, go. Or how's there, any questions? Okay, just go. Go. Are you crushing it?
Perfect.
Awesome. Are you crushing it? Are you trying to weights? Are you going to come up and how would you run this? And take your free time down.
Are you available when you do this? I think this goes absolutely. Gives me the data and that's the use. pretend I'm at conception. See, I would say, like, when we told our research, like, before I was listening to podcast, I realized literally this is my final, like, my senior spring semester, the final, I can finish all of my school that I stuff in, and miss most of it. The Willamette University is missing. I miss my college. And I can't fix it because every other, like, final class I'm getting back. So I was worried for something that learns that I will be forever ruined. I have to have all my student files.
Well, you actually missed one. That's hilarious.
There's literally everyone. Yeah, there's still everybody. There's a people.
Oh my god.
I was surprised how small it was.
I can see them. I also grew up on the coast, so. Ooh, water. Oh my god. I have accidentally written somebody once, Tina out this year, I'd like to keep it. Let's see how much that's. Okay, well I guess that's what I named mine too.
I just saw the option based around and I went and decided the answer to the I could.
No, change it. That's why I changed it.
Oh, I just,
They got that wrong, but then the next one.
I'm gonna finish off with my
So this is like the
It's dinner time, go eat. We're probably not calling back until like this time.
Yes, they are.
Like I saw them, I thought of you, and I had to get them.
It's just putting out all
Only one. That's the kind of day I'm like. I took him out of the shower.
Yeah, it's like we're not saying it's true, it's gonna be wait for whatever.
So you got the weight. Oh my god. I always forget she's an NBA student until she says something like that.
So that's what I did.
You know what I mean? Like, the closest I would probably get to Anaheim in the next 5 years is probably two people, which is like an hour and a half.
I always thought it was just like,
I love it. Is it only California? I've always wanted to go. So I've been to San Francisco, like passing through, or like stuff, and I've always wanted to explore. But
not really a story, but more like, this is what I'm
That's the story of my life. Where did it go? Yes, it did. It did auto-generated.
There's all kinds of trails that you can follow. It's like that is also because
do you know they built the Hollywood Museum? Is it Berkeley? screens. Oh, apparently the sign was unaffected by the virus, even though it was like running around. Literally, what do you mean unaffected?
It's literally on fire.
There's no. It looks very effective.
I have,
Yeah,
to my
right.
knowledge, I don't have.
Okay, well,
So like, I always have a plan. Oh, we can each step in the right time. All the stuff. It's just a large number. And very frequently. Probably something special. So don't worry about that. That's what we want. That'll be just not fun. That's fine, but I. I didn't know that said I had it.
The main concern with that one is working professional. I mean, I give you
Not everybody.
Josue, Nicole. But the change from electric stuff to the track was also.
Yeah, really, right. Many of the classes.
Okay, cool. But, because I know that they do anything where this percent, you know,
They are no longer advocating that's a division, it's a division decision made by
yeah.
Yeah, because the original problem was I would also argue that there's plenty of want for it.
This all arose from an original plan. And from that,
Yeah. They really took that ion and left everything else.
Right. Women's program.
finished, then.
Yeah, it just like, he's enforced or something goes the whole time, and that's not something that's feasible for a lot of people.
The sentiment that I hear echoed here in Hong Kong, except for the it's just kill too much. Very boring what he said.
But I didn't get Worthington principal one. Other schools, voices. At one point I was up for three, but then I lost three. There were 3 games for all. One won to 2-6. I mean, the fact that we got up 14 was ridiculous in the first place, so I'm not mad at that point.
Yeah, no. Yeah, that's so great.
I heard the word politics. This time last year, it's also something to do with I don't fully. At least if I remember correctly.
Is that for service songs? Oh, okay. Okay.
And I think the other was because we changed the designation to students that need more credits in the last semester. Because I technically were those two.
Awesome. I'm really almost like crazy. I get like that, that's
It's all been changing over time, so it's nice to see.
We don't want to make our Today I just found out that still one summer. But it's summer. Laura.
That's what I think. Are we all here? It's go time. Does anyone have any questions on this exercise? If I were you, and I'm me, and I did do this, I wrote a function that, given one of these things, takes a data frame, computes the weights, loads the weights into a data frame, and calls it weight train, right? So I could say data equals train, and then right here I could say weights train province, and it just grabs everything. And then I never had to think about this again, because I don't know how much time you spend thinking about this, but like in my sort of like high performance extreme computing cryptography class right now, we're going through the process of figuring out that computers are dramatically worse at division than they are at everything else, right? And I like to not think about division for that reason. I don't believe in fractions. I only believe in the integers. I'm not even convinced that natural numbers exist, right? I've never seen -2 of something, right? Right? If -2 were out there, we would have found it by now, right? I often have a negative number of dollars, but dollars aren't real either. So you can think about this however you like, but ultimately what's going on here, right? You find the max, you divide the relevant one, or you divide the max by the relevant one, and that's this thing, right? And so that should not be 3, right? But there was some rounding in here or something. I don't know. I think I did this by hand because I didn't want to have the answer key in here. Okay. Does everyone, okay, I don't know if you're all like gasoline-powered internal combustion pilled, and can I hear it for gasoline-powered internal combustion engines? Yeah. We were talking about the Yankees earlier. How about we talk about Daddy Yankee, right? Gasolina, absolute banger. Do you all know Gasolina? Yeah, okay. I'm not going to try and sing Gasolina in front of all of us, but I want to. So we're going to be regular, which is the crate of gasoline that I put in my Honda Fit, right? This is regularization. Okay, so we've made a lot of models in this class, right? We've made a lot of fits, we've made a lot of predictors. We've used a lot of different methods, right? Some of them are complicated, right? Sometimes you take like thousands of words, probably not millions, right, but hundreds, right? And you have a coefficient for every single word, right? You're really predicting whether a wine comes from California or not based on whether it has the word not in its description. Get out of here, right? We got rid of some of that stuff with stop words, right? But maybe it makes sense. Maybe you've thought about this before. You thought, do I really need all of those features? Like, what if some of those features are just like not that important? Maybe they have like really small coefficients, right? Maybe there's a bunch of them, or maybe they don't have very high predictive power or something, right? So one way we can do this is we can apply a penalty. And what is the penalty? So this term over here. This is a penalty function applied to the predictor function. And we want to minimize the combination of the error. So this is the difference between the predictor. Do I need to go back? Okay. This is the observation. This is the classification or the value. So this is the difference between the prediction and the actual. And we want to minimize that difference. But we also want to minimize how much drama there is going on inside this predictor. And there's two ways to minimize the drama. You all have probably heard of Occam's razor, which is that, like, the simplest explanation is, does anyone know Occam's razor? Yeah, what is it? Yeah. Right, so like, we all know that the sky is blue because B is alphabetically first within the colors, right? It's the simplest explanation, that's why it's correct. That's a bad example. Okay. I'll just leave it at that.
But it was simple.
So some of you try not to talk about grades too much because I'm not like trying to get fired, right? But like I realized that if you want to have zero disparities in grades in your class, the function return A produces zero disparities, right? It was the simplest grade, and I was like, wow, this has fantastic features, like really high equity. I have higher equity than anyone else, right? Anyways, can I hear it for the A's? They just moved to Las Vegas, right? Yeah, woo! I don't even know if Las Vegas is still controlled by the mob, but I hope it is. Okay. So sometimes you care more or less about simplicity, right? Here's an example of a time I don't care about simplicity. My name is Netflix, and I am predicting what show you want to watch next. And if I am 0.01% more accurate, I might make $15 next month, right? And it costs me 0 cents to use 1,000,000 instead of 100,000 features. Essentially no difference at all in computational costs, right? So the Netflix Prize dataset was one of the first datasets where it was like, sure, we'll put in a feature for every single video on the Netflix platform, and we'll just throw it in the machine learning algorithm. It'll be fine, right? I think the people that did a protein folding problem, they did not care about how complex the model was, right? They were modeling a biological system without knowing any of the actual laws of biology. They concluded every single piece of information. They had no penalties for complexity, right? Here's an example of when I care about this a lot. If I ever have to explain anything I do to anyone, and they say, why does your model have 3,000 coefficients? Can you tell me what a single one of them does? And the answer is, no, absolutely not. I have no idea what a single one of those coefficients does, right? So oftentimes, if I have to go to my non-technical manager, which is redundant, pretend you didn't hear that. Sorry, that one just slipped out. The simplest explanation is that I haven't had my coffee yet. Okay, all right, moving on. Okay, so like if you're a manager, you manage people, that's inherently a soft skill, right? Like we can accept that, it's by construction. Okay, so I oftentimes put extremely high penalties on complexity in my model because I'm not actually trying to predict things accurately. I'm trying to understand what underlying mechanisms are at play, right? So something I've been very interested in for a long time, right, is the degree to which the zip code in which you are born predicts how much money you will make when you are 35. And it is an extremely strong predictor. And this is interesting to me because I'm interested in what is the shape of the United States economy. You know, how do I serve different students? How do I have, you know, different industrial and economic policies? If I'm trying to, for example, reorganize the nation state around having 2.5% annual growth instead of 2%, how do I do that? And my opinion is you do that by teaching night classes in a Master's of Science and Data Science program, right? But other people have different opinions. And so when I was looking at the US economy, I was not, in fact, interested that there were many other features that had very small predictive powers of how much money you would make when you were 35, right? I saw that what basically mattered is how much money your parents made when they were 35 and what zip code you're born in. And then like things like gender matter a lot too, and no one's really happy about that, but it is important to acknowledge it, right? And so what I didn't really care a lot about was whether or not that was associated with your blood type, right? That one was kind of uninteresting to me. And so frequently when I am trying to understand what is going on in the world, I value simplicity very highly, right? I want the absolute fewest numbers of features that enable me to think about things and reason and to understand, right? So that's when I use very high penalties. We can set how much penalty we want, which is how much complexity cost there is, how much we're charging for complexity, right? Using this lambda term. The lambda term is fundamentally in conversation with the notion of error. We recall error. When I predict something and I predict it incorrectly, I have to pay some cost of correctness, right? And usually that corresponds to a lower kappa score or anything else, right? And you all remember least squares lines. How much do you know about least squares lines? Like 7, 10, 0, 1 out of 10? How much do you know about least squares lines? 4? Okay. So I got some data sets. I'm plotting on one line how cool you are, and I'm plotting on the other line how many YouTube subscribers you have, right? And so there are many people on this, well, not people, in fact, they're Google accounts, which don't correspond to people, right? There's many data frames, but the cooler you are, the more likely it is that you have a large number of YouTube subscribers, which is how we can tell that Mr. Beast is the coolest, right? Can I hear it from Mr. Beast? That was a test, you passed, good job. I thought I should name my YouTube account Professor Beast. Do we just feeling that out? I'm getting some no's and I'm getting some hell yeahs. So I feel like the hell yeahs are out. So I plot how much coolness, which is measured by your number of Instagram subscribers, of course. Or wait, no, are they called followers on Instagram? Okay. So you plot Instagram versus YouTube, right? And you have some line, and you measure the distance from that line and square that. The line that has the least squared distance is the best line. Now we are adding something else to that. We are willing to give up some of our least squaring in exchange for having fewer dimensions, right? So when we have Instagram followers versus YouTube, no. Followers, subscribers, why is it not the same on every platform? We could add other dimensions. And so my favorite social media platform is LiveJournal. We all remember LiveJournal, right? Is anyone else 47 years old? Yeah? Okay. I don't know if anyone's actually 47 years old, right? But so I think LiveJournal was popular in like the late 90s, right, before the dot-com bust, which is when the big mistakes were made. We should have just stopped using the internet after 2001, right? But we kept doing it. And so if you're on LiveJournal, right, that can be a third dimension, right? So we can have in this dimension Instagram, in this dimension LiveJournal, and in this dimension YouTube, right? And perhaps what you find out is that your number of LiveJournal subscribers does not strongly predict your number of YouTube subscribers. I would expect to find that, right? So we can apply a penalty and then apply a 0 term to that coefficient, right? Force that coefficient to 0 so it falls out of our model. And this might cause our model to be slightly less predictive, but it might be more explainable or it might be more useful to us. Let's look at a little bit more mathematics. Okay. We all love mathematics, right? That's what I thought. Let's start with this term. We're going to start on the right-hand side. What is that? B sub j. B sub j is the coefficient, how much we multiply, the value in the jth column. So for example, in my coolness ranking, I could have 4 columns, right? The first is name, so we've got Conrad Beast, right? And then the next column could be YouTube subscribers, and the next column could be Instagram followers, and the next column could be LiveJournal followers. So perhaps B sub LiveJournal will be a very small but non-zero number, right? And so B YouTube subscriber might be very high, and B Instagram follower might be very high. So we could have some large values here, and we could have some small values here. We sum up the absolute value of all of those coefficients because perhaps being really popular on Tumblr might be negatively correlated with being cool, right? That might make you like niche or edgy, right? And so if there are a total of P features, then we sum up all of the features and we add up all of their absolute value. And we multiply that by our penalty term. And we are trying to make this thing as small as possible along with this thing, right? So what's this previous summation, right? Well, the outer part here is from 1 to n. And what do we have n of? We have n observations. So this is how many accounts there are on YouTube. So you've got Mr. Beast, you've got Dr. Beast, You've got, I don't know what other beasts there are. Mid-beast. We got wildebeest. We've got Jenna Marbles. I don't know, that's the only person I can think of, right? Okay. Well, we love Jenna Marbles, right? I think she canceled herself, and we respect that, right? I should have done that. Okay. This is the actual measure of coolness, right? This is the known level of coolness, okay? What is this thing, B sub 0? Well, our coefficients, they started at 1 and went up to P, right? This is the intercept in our model. This is the base level of coolness. So perhaps if you have 0 Instagram, 0 LiveJournal, and 0 YouTuber followers, you still have a coolness level of 0.7, right? And you fought for every point of that 7, right? And so this is the point, this is the baseline coolness of someone that doesn't have social media. So that's how cool you are if you touch grass, right? And then, what do we have here? This is how we are making our prediction. For each one of the features, we take the coefficient that we determined from our training, and we multiply that by the observation. So this is the ij observation. What is that? I refers to this number. That refers to the observation number. So that refers to Mr. Beast, Mid-Beast, Wildebeest, least, yeast. I don't know. Okay. There's probably like some really big like sourdough yeast YouTube. I bet there's like a Mr. Yeast YouTube channel. Okay. If you're from the lesser of the two coasts, you could be Mr. East, right? I had a, sorry, I'm completely off task. I had a social studies teacher named Mr. East and I had a science teacher named Mrs. West and a social studies teacher named Mrs. East in middle school, which is very odd because East and West are socially constructed, so traditionally you wouldn't learn about them in the sciences. Okay. So x sub I, that is the ith person who has some YouTube, Instagram, and LiveJournal account. And j is the jth feature. So that is either the YouTube followers, YouTube subscribers, Instagram followers, or LiveJournal followers. And why did I pick something where there's followers and subscribers, right? I worked this all out in my head, and I was going to do Twitter and Instagram, right? Because they're the same. Okay, so this predicts. This is your predicted value alongside the coefficient. And so this is the actual value. This is for numerical data, right? We're not doing classification here, right? So we predict 0.8 coolness. We subtract 0.7 coolness. We have 0 of everything, so there's nothing here. We square that. So this is the squared error for one observation. We take the sum over the squared errors for every observation, right? So this is the squared error. Okay? And we're not square rooting this, by the way, right? So this is not the root mean square error. This is the square error, the sum of the square errors, right? We take the squared error, or the sum of squared errors, and we add it to the penalty. And we're trying to keep that as small as possible, right? Now we introduce lasso. I never remember what this stands for, so I'm just going to have to read it. The least absolute shrinkage and selection operator. You use lasso, which is a method that is applied to the selection of coefficients, okay? We're creating a model, we're creating a linear model, we're producing coefficients as we always have been to produce our predictor. We're going to modify our predictor to be more simple. It is going to cause the regression coefficients to tend towards 0. Why is it doing that? It's penalizing distance from 0. The absolute value is how far something is from 0. When this number goes up, it is treated as if the error is higher, so we are disincentivized from having coefficients. The lasso method uses a penalty based on something called the L1 norm. The L1 norm, this is wrong, right? That's L0. I learned about the different types of norms in a class called real analysis, and essentially all of them are based on this notion of different ways of evaluating absolute value, right? When we have, for example, the point in the xy coordinate plane 1, 2, there's different ways of measuring how far that is from 0, 0. We can say, for example, it is a distance of 3 from 0, 0 because we move 1 in the x direction and 2 in the y direction, right? Oftentimes we don't think of it that way. Oftentimes we think of it as along a hypotenuse. So if we progress directly from 0, 0 to 1, 2 along the hypotenuse, we get the square root of 5 distance. Is that right? Does anyone know how hypotenuses work? Yeah, you nodded. Okay, I believe you. Square root of 5. And the square root of 5 is how much exactly? Okay, so let's say speculatively it's 2.3, right? We should do some mental math, right? It's 8:35. This is prime time to do mental math. Okay, so 23 squared. So if it's 2.3, right? So that would be 4 plus 0.3 times 2 twice, which is 0.6, and then 0.3 times itself, which is about 0.1. So that's about that's about 4.7. So it has to be between 2.3 and 2.4, right? What's 2.4 times itself? 2 times 2 is 4. 2 times 0.4 times 2 is 0.8. 0.2 times 0.2 is 0.04. Why am I doing this mentally?
You just said it's prime time to do mental math.
Well, then I tried to do it and it was really hard. What? I was off? Look at this. Look how wrong I was. I'm not even close. Do you believe me when I say numbers in this class? That's humiliating. Okay. You all like hung out doing mental square roots with like your friends in middle school, right? That was before we knew about proofs. It was the only math we could do. Okay. So in practice, what is lasso regression going to do? Well, essentially, at high probability, it's going to find some large number of features that just don't matter that much in the grand scheme of things, right? So Netflix is not very good at predicting what I want to watch because the only thing I ever want to watch is Nosferatu 1922, right? Which we can all understand, right? Why would we watch other films when we could just watch Nosferatu 1922 again, right? And so when Netflix is predicting what I want to see, they should assign a 0 weight to everything I do except wanting to watch Nosferatu 1922. And the way you can tell if someone wants to watch that is their second favorite film is Scott Pilgrim versus the World. I know this because I conducted an experiment, right? So you really only need one feature to predict what someone wants to watch, right? Now, in practice, most data we collect does not affect the thing we are trying to study, right? Or it doesn't affect it in a way we can discern or predict or use or apply, right? So if you are not adding that much predictive improvement to the model, the penalty, which is the lambda term times the size of the coefficient, is bigger than how much you reduce the square error by, right? Here's another thing to think about. So I was just doing a square root cognitively not very well, right? When I multiply decimal numbers by each other, those decimal numbers get smaller, right? So whatever our sort of numerical base is for our model, once the line gets in within one of them, that square error is going to be quite relatively small because squaring is going to make it seem actively smaller, right? We have very low penalties for being relatively close to our prediction, right? So it's quite easy if you have any sort of reasonable coefficient at all to drop that coefficient to 0 or very, very close to 0. You have seen other forms of variable selection. Do you all remember the variable importance graphing, for example, right? And then also when we did the KNN introduction, we went through different features and saw which ones contributed more and less, right? Lasso is a systematic numerical, specifically numerical, right? Numerical way to select variables. This is a very useful thing to do. Very frequently, we do not want to be passing around large numbers of variables or features or what have you, right? We want to have relatively simple, explainable, understandable models because we have to explain everything we do to our non-technical manager. I am recommending, and I had to look into this a little bit because it looked like some of the stuff that was used in previous years maybe did not work anymore. This thing called GLMNet. Have any of you used this before? Glemnet, right? I guess I would pronounce that Glemnet. But this is for lasso and ElasticNet regularized, generalized linear models. So generalized means a variety of ways to conduct a linear model. Regularized means has penalties. Lasso is the one we just introduced, and ElasticNet is the one we're introducing next, right? So I included this in my sort of libraries. I think the library is called GLMNet. And there's already a GLM. There's already generalized linear models. We've already seen that, right? So this is just generalized linear models with net, okay? And you just specify inside of your training function, perhaps, or I think you can just use GLMNet directly. And this is going to require one additional parameter to our training method. And that is going to be something called the alpha value. Now, I've been trying to reduce the degree to which I am throwing large amounts of mathematical notation and formulas at you, but alpha value is another coefficient in sort of our cost function. So we have our square error, we have our coefficient cost, and we're going to have one other thing. That other thing is by default set to have a 0 weight on lasso. So we specify an alpha value of 1, which multiplies a 1 by our lambda summation of the beta coefficients. We are going to use non-1 alphas on later slides. Just be aware of that. I looked for a way to introduce lasso without having the alpha value, and I couldn't get anything to work in R, so I had to introduce this sort of out of order. I apologize for the complexity. I didn't know an extremely cool and fun way to do this, so I used an expand grid, whatever that is, and I set alpha equal to 1. Tune grid is, I think, clunky, but we only use it here as a demo. In general, my impression was that you can sort of just leave out tune grid, and GLMNet is going to basically guess what you want to do, and it's going to guess you want to do ElasticNet, which is, in fact, what you almost always want to do, right? But I haven't taught you what ElasticNet is, right? So we're going to look at lasso first. By default, these lambda terms are going to be quite small. It's my impression. So this is our best tuning, best lambda. It's very, very little, right? And why is it very, very little? Well, we probably have a lot of coefficients, and they could be very, very big, right? So we might not be multiplying them by that much. Here is the confusion matrix. Let's just take a look at the kappa value. Not bad at all. That is a generalized linear model with a very small but non-zero lasso. We don't have that many, I think, predictors in here. Where are they? Oh, I should be looking at the coefficients, and I don't think I have them printed out. But let's look at this kappa, and let's appreciate that that is a rock-solid kappa, right? Very good. And nothing too exciting going on here. We have a province, we have our training set, we're using the generalized linear model with lasso, and then we're using the same control that we used earlier, right? So that's the control we've been using all time, 5-fold cross-validation. Same thing that's going to be used on the modeling project, okay? I know what you were thinking. You were thinking, Calvin, why did you introduce the L1 norm? Well, because I was about to introduce something else, which is the L2 norm. The L2 norm corresponds to bridge regression, and instead of using absolute value to make sure that your coefficients are positive numbers, we are going to square the coefficients. This thing is exactly the same thing as in lasso, right? This is the actual value. This is the predicted value from the coefficients. This is the predicted intercept. This is the coolness of someone with no followers, which is 0.7, as we all agreed, right? We square the whole thing. We do this for every single one of our observations. And then the only thing that changes, instead of absolute value here, we have squaring. That's all. What does this do? Now we don't have a very high penalty for very small coefficients. This means many coefficients will persist in our model at a non-zero level. Pros and cons, right? This also means that if you have big coefficients, they cost you a lot. So this prevents coefficients from getting too large unless they really need to be to drive your error down. I think this is pretty cool. My impression is, I've never heard people talk about Ridge. I only ever hear Lasso and ElasticNet. My intuitive sense is that this is almost always what you want, right? It doesn't make sense to me that you would care the same amount about a change of 0.1 to a coefficient that is a million as you do to a coefficient that is 1, right? It seems like that squaring helps sort of change your analysis for how big of a change something is to be relative to the size of the coefficient rather than relative to 0. I don't know that that actually works in practice, and when I used this thing, it didn't seem to pan out. But I tend to not want to assume that everything should be linear. I think what I actually want is this probably to be exponential, personally. But that's probably a little bit being computer scientist build. Okay. This is also called Tikhonov regularization, named for Andrei Tikhonov. I spend a certain amount of time in all of my classes pointing out that things are named after people, and this is frequently a strange design decision. The Turing machine is named after Alan Turing, who is probably not the first computer scientist. That was probably Ada Lovelace or possibly someone considerably before that. And that's just within Western Europe, right? There are a lot of things in a lot of computer science, data science, and mathematicians that are named after the first Western European to discover them, who was a man, right? It was very surprising to me when I looked up ridge regression that it was very obviously discovered by a Soviet mathematician, and that it was referred to as ridge regularization instead of by this person's name, because there is a ton of things named after people's names all over the place in mathematics. I would like you to have some sense of analysis of this is the first time in my life the entry-level categorization for something named after someone doesn't have that actual person's name in it on Wikipedia, which I treat as ground truth. And to my knowledge, this is one case where this is very obviously a Soviet mathematician. I gave the example of a Turing machine. I believe Emil Post was a Soviet mathematician that discovered the Turing machine literally the same month as Alan Turing, whose name essentially did not exist in history books. I don't really know how science and technology was happening in the Soviet Union in the 60s or whatever, but it does seem like they were doing something over there because they had a space program. So I don't know a lot about that. Think critically about what things are named after. Do your best to be engaged in all of that stuff. Okay. There has not been a Soviet Union in my lifetime. Okay. Shrinks the regression coefficients towards 0, but not as aggressively towards 0. Mostly it shrinks them to be less than 1. The L2 norm is just the squared distance. Does anyone here know what norms are? I think I'm describing my norms incorrectly. This is wrong, right? Okay, none of us know. Anyways, it's the L2 norm. I have no intuitive sense for what an L2 norm is. To me, it's just a mathematical object. Okay, I'm back to my alpha grid. So I had something previously called Lasso, and Lasso had an alpha of 0. At this point in time, you may realize that the alpha measures the weighting, because we've done weights, and that's why I taught this the same day as weights, of the squared and the absolute value term, right? So we apply a 0 to the Lasso term, which is absolute value, and this causes correspondingly there to be a 1 multiplied by the ridge regression or the Tikhonov regularization. I take the same lambda sequence, blah, blah, blah. All of these operations are the same. We just do ridge regression. Much higher lambda, 12 times higher. Why is that? I expect the squaring causing small numbers to be very, very small is causing this change. Let's look at our kappa value. And we'll see it is actually a bit lower. So in this case, is it ridge regularization? I keep saying it wrong. No, it says ridge regression, right? Have any of you heard of this before? Ridge regression. Yeah, it is called ridge regression. I keep wanting to call it regularization. Okay. Ridge regression, not as effective at driving high kappa values as lasso regression. Okay. Where's the alpha term? This is where the alpha term lives. Okay. Let's decompose this. Elastic net is the combination of lasso and ridge or Tikhonov. Same features, same observations, same coefficients. This is just an addition with alpha. And I call this lowercase alpha. I say what alpha is. I spent a lot of time in classes, sort of at the beginning of undergrad, seeing a lot of Greek characters and not even knowing how to refer to them. We're using alpha here because that character is not already used. It is commonly used in practice, which we can verify by the expectation that we call something alpha here. And if I wrote out alpha, I think this would also be miserable to read, right? So that is an alpha times the lambda. Those are both Greek characters. I can't do anything about that. We have the alpha value, which ranges from 0 to 1, and we multiply the lasso cost by alpha, and we multiply the ridge cost by 1 minus alpha. That's all. What did I click? What am I doing? Oh, here's elastic net, right? I clicked something, right? Okay, this is elastic net. Sorry. I've literally only ever heard of lasso and elastic net. I don't know if it's because ridge is known by 2 names. I don't know if it's because it's generally ineffective. To me, it makes intuitive sense, but I don't see it around. My recommendation, and I think this won't ever cost your computers too much money, is to just try a few different alpha values and see what works. You can just try 3 of them pretty easily. 0.51, done. That gives you a lot of sense, right? Should be relatively simple. Obviously, using an alpha value that is not 0 or 1 will be slightly more expensive because you will have to compute additional information. It's not that expensive, right? There's, generally speaking, going to be many, many fewer coefficient calculations than there are each observation calculation because you have to evaluate each coefficient for each observation. So that is p times n cost, whereas the cost functions only cost the number of coefficients. I really liked this. I no longer need my tune grid. If you just throw glmnet directly into train, it just works, and it just does elastic net on its own. That's really nice, because I didn't like messing with the tune grid. We can think of lasso and ridge as advanced topics, which the R language obscures from us, lest we learn too much about them. I have seen lasso written on way too many job ads to not tell you what it is. So I'm telling you what lasso is, and now I'm telling you never use it. Use elastic net every single time. We find the optimal alpha, which is 0.1. So what does that mean? 0.1 times the absolute value term. So this is very, very ridge slanted. And this lambda value is larger than the lasso lambda value, which was 0.001. And it is smaller than the ridge lambda value, which was 0.012. So I have an intermediate lambda, and I am very slanted towards ridge regression. Let's see. How much better is this? It's not. It's roughly the same as lasso. I think this is why I see lassos so often. I guess on whatever types of data sets people are using. Frequently, lasso is performing about as well as elastic net, and perhaps elastic net is perceived as more complicated. It is worth noting that we sort of motivated this whole thing by Occam's razor, and then we generated a square of a summation summed minus an alpha value times another summation plus 1 minus an alpha value times another summation. So we could argue that maybe we are not actually valuing simplicity as much as we want to be, right? my recommendation in general is once you're using the computer to do data science, you should use the computer to do data science. You should plug in ElasticNet, ask the computer to select the best lambda value, and then go to the water cooler and ask your boss for a raise, or whatever it is you do at the water cooler. Do people have water coolers anymore? I remember the water cooler in my first job. I was making hard drives in Longmont, Colorado. We had a water cooler. The water was room temperature because the cooler, of course, broke. It was a good time. Anyone love hard drives? Yeah. I used them to store Nosferatu 1922 on them. Okay. In CS 151 last term, I gave an entire week of lectures on the Alien franchise. That is a real thing I actually did. Okay. What am I clicking? Did that say page not found? Huh. Oh, I didn't put the URL in there. I just copied the exact text. Well, let's see if we can find it. You should never trust me. There, we found it. I don't know who Fort Monroe is, but I guess we trust this person. Anyways, I found this graphic on the internet, and this graphic is used all over the place. I've seen this a gazillion times. It was in Professor Katada Smalley's tenure talk, actually. And she got tenure, by the way. I don't know if you all heard that. Congratulations, right? Yeah, let's hear it. Couldn't have happened to a nicer person, right? Okay, so, anyways, this is very interesting, and I'm going to be extremely obnoxious. This is not an image because you can highlight text in it. And I had only ever seen the image representation before. What is this thing? So, let's see. View selection source. This image was generated not in like a graphing library or anything. This is just HTML. These are SVG elements of fixed heights with fixed borders. This absolute lunatic invented bullseyes in HTML. Look at this, specifying colors. What a hero, right? So I'm humbly submitting as evidence that you should care a lot about HTML. That
Making circles is hard, let alone circles are center. You see the puzzle?
yeah. Sorry, what? Let's find out. Let's see how truly excellent our hero is. Let's see. I don't know. This is looking pretty good. Can someone open this on a phone? Okay, there we go. We did something cursed there. I don't know what this is, but it looks bad, right? Okay. I never thought I'd say this. Everyone get out your phones in class. Go to this website and see what it looks like. What's this called? This is called Understanding the Bias Variance. I don't know how phones work. Oh, gosh. My keyboard's not loading because on a cell phone you have to have internet connection to have a keyboard. Fort Monroe Bias Variance. Looks pretty good on here. I don't know. I don't know if you can see that. That's a bullseye, right? It appears to have low variance and low bias, as we all strive to do. So, I think this is what the kids like to say is based. So, thank you. Thank you, Fort Monroe, for whatever this is. Learn HTML. Okay. What is the purpose of the introduction of the bias variance trade-off, right? Or I'll speak while I have this graphic up, right? If we predict something, and we always predict 20% too high, we have to put on our clown nose and our clown shoes, because we've completely beclowned ourselves, because it is really, really silly to predict 20% too high every time. And that's what bias is, right? We don't want to always have a miss in the same direction of similar distance, right? Separately, we might care a lot about being very precise, being perhaps the same distance from the absolute value, from the actual value every time, right? And that corresponds to low variance. In practice, we usually have to choose a trade-off between these two things, right? We might be skewing our model in one direction or the other to get this sort of lower variance that we're striving for, right? To have all sort of our predictions clustered where we expect. As a machine learning researcher or scholar or whatever you're going to do when you grow up, if you grow up, fight it. I'm still in school and I'm however old I am, right? And so you can keep doing this forever too. You will have to make decisions about the trade-offs between these two things. And there's no right or wrong way to do this. Just be aware that there are costs involved. We have two mechanisms to do each of these things. We can reduce variance via bagging, which stands for bootstrap aggregating. And we can also reduce bias via boosting, or sort of a feature selection thing. Intuitively, I think of this process in the following ways. I introduced at the beginning of class today the notion that you take a data frame, you throw it in caret train, and you get out a predictor. It may occur to you that you can take, for example, a linear combination of predictors. Perhaps you can use both random forest, nk and n, and use them both to predict, and you can perhaps add some weight to them. Or perhaps you can do part of a decision tree, and then after you ask a few questions, fall into a naive Bayes algorithm, right? All of these things can be done, right? It is simply a matter of writing the code that does them, splitting up the data frame, and so on. That is the intuitive sense behind this bagging and boosting technique, and these are usually referred to as the notion of ensemble models, okay? So, we have also used, I think, the notion of resampling most commonly with Bootstrap, right? We can take a model, take some subset of the information from our training set, train the model, and assess over the remaining of our training set. And we can do this iteratively over time to get progressively more accurate coefficients that have lower and lower errors, right? That is one way to get more refined measurements and predictors, right? Separately, we cannot fiddle around with what particular observations we're providing to a predictor or a training algorithm. And instead, we can average the predictions from different models. So instead of changing what observations we provide to one model, we change what models we provide to a predictor. It is a higher level of analysis, right? And we can sort of combine all of these things, right? So we can do resampling within one model and then apply different models together and take combinations over them. And this is going to essentially help us fit more and more precisely. Let's look at bagging first. Bagging stands for bootstrap aggregating. And I think you all remember the bootstrap as an alternative to k-fold cross-validation, right? K-fold cross-validation was very precise, making sure that every subset of the data was used exactly the same number of times, and Bootstrap just threw caution to the wind and just took different observations and trained over time, right? When we are bootstrapping, it is relatively simple to do this step. Make many models. Many models. The more models you have, the more likely one of them might be correct, or accurate, or powerful, or useful. Or perhaps it is wrong in a very specific way that is corrected by another model, so we can combine them together. So we use bootstrapping here to get a diversity of models and then combine or study or integrate those different diversity models into one sort of super model that solves all of the problems. We can combine with either voting for classification, and why do we vote for classifications? Well, there's no real way to average Casablanca Valley and Marlborough, right? We just have to see which one is more popular. But we can also average things, because if we have a bunch of people that assess a wine as a 94 and a bunch of people that assess a wine as a 96, we can just say that wine's a 95. Some of you may have heard, not to brag too much, but my personal emergency backup hometown after Salem, which is Portland, has the rank 34 international coffee shop in it, which is Pushpull, right? And that ranking was an average of different reviewer scores, right? They didn't have to classify it as 34. They didn't have a bunch of votes and some people voted for 34 and some people voted for 33. No, a bunch of people submitted scores and then the scores were aggregated to produce a super score of 34 overall, which is actually a ranking, right? And then there's this other coffee shop named Proud Mary that's actually based in Australia, but they have a cafe in Portland and it did better. But we don't like Australians. We only like New Zealanders because they have better wines. Okay. Blah, blah, blah. Voting, majority, something, something, democratic institutions. Okay, all right. Bagging. The sort of most obvious bagging method I found for us all was tree bag, which is a bag of trees. I have nothing clever to say about that, but I do think it is funny to think about having like a grocery bag full of oaks, right? And then there's probably also like a weed angle in there, but I'm straight edge, so I don't know about that. Okay, so what we can do is we can generate a whole bunch of trees. Y'all remember decision trees? Does your description contain cherry? Does it contain noir? Does it contain 2017? Does it contain fruit? Does it contain tannin? Does it contain crisp? And you don't really necessarily know which one of those trees you want to go with, right? Like, you can do some training process and arrive with a tree that's pretty good. But maybe it would be better to have a billion trees, right? And to just multiply or vote the results across all of them. That's what this does. We have k-fold cross-validation. Can I scroll? No, we can't. Why is this not working? Did I break my computer? There we go. Kappa, 0.66. Some things to point out here. Different sample sizes, but those are all within a rounding error of each other, right? I only did 5 iterations, which means I could have iterated many more times and got markedly better answers. And this is already a pretty good kappa value, right? This is competing already with elastic GLMNet, which is a pretty good method, right? So this is a good way to solve problems. Bagging is good. Bagging does not always have to only be done over trees. There was a built-in R language way to do it over trees. I am not accustomed to seeing bagging that often. I always see bagging and boosting together in ensemble models, and we will get to that, but this is a built-in way to do bags. Separately, you are aware you could train a model many times, take all of the fits, multiply them by each other, and make some aggregate prediction over them. I actually had slides where I did all of that. I took them out because it looked heinous, right? But it is possible to do that. It's not even that hard. And I produced, for example, a method that took random forest, KNN, and naive Bayes and just multiplied them together, right? It was fine. It wasn't that bad. This is what the outcome looks like. We got our kappa value, 0.66. This has all of the usual features that all of our predictions have, where they love Californians, because don't we all? We love Californians. Okay. Look how much text this is. This was on the slides that both Jameson and Hendrick had, but I think it's a good story. So I'm going to try and read this out loud, and I'm going to try and make it fun while I read it. Okay. So all of you, I'm sure, are aware of horse races, which are races in which a human tries to run faster than a horse, right? Okay. So I have a horse racing gambler, which is someone that thinks they can outrun a horse, right? And this person is hoping to maximize his winnings and decides to create a computer program that will accurately predict the winner of a horse race which I would always guess the horse, based on the usual information. And so what is some of the usual information? Well, perhaps you might know how often this horse runs faster than humans. Perhaps you know how often this human runs faster than horses, things of this nature, right? Perhaps you know the Las Vegas odds for the horses and humans, right? Whenever I'm trying to decide who's going to win an election, I just look up what the betting markets are in Vegas, and they've never been wrong. But Nate Silver is wrong a lot, and he has a PhD in statistics from the school I went to. To create such a program, the horse racing gambler asks a highly successful expert gambler. Can I hear it for our highly successful expert gamblers? That's what we refer to as someone with a problem, okay? Right? But, okay, no. Everything is only a problem if you lose, right? Like, it's not illegal unless you get caught. Okay, so you ask the highly successful expert gambler, which is a gambler that has not lost yet, probably through survival bias, to explain his betting strategy. Not surprisingly, the expert is unable to articulate a grand set of rules for selecting a horse. Why is that? Because this person is only an expert gambler through survival bias. They don't have actually any underlying methodological evidence, right? Because if they did, they would be cheating, right? Because no one actually knows who's going to win horse races. Perhaps you have all heard of the great story where you can take any given, I think called like stockbrokers or something. Does anyone know how the stock market works? But anyway, so I think like if you run a hedge fund, right? There's all these people that are like considered successful hedge fund managers because they correctly see hedge fund growth for like 8 consecutive years, right? And roughly 1 in 256 hedge fund managers are in this category because the odds of correctly going up every year for 8 consecutive years is almost exactly 1/2 to the 8th, which is 1 over 256, right? So at 50% probability, every excellent stockbroker or hedge fund manager does very poorly the next year because they were actually only doing better than the odds by coincidence, right? Anyways, I always beat the averages. Okay, I've been getting away with it so far. Okay. On the other hand, when presented with data for a specific set of races, the expert has no trouble coming up with a rule of thumb for that set of races, such as bet on the horse that has recently won the most races. This is known affectionately as having no idea what's going on, right? So, right, if you really know what you're doing, you would know the coefficients on each of these things, right? But the expert gambler does not actually know the coefficients because if they did, they would be Vanguard and not a hedge fund manager, right? Get a job at Vanguard, by the way. My first friend to get a job with a data science job title works at Vanguard, playing with $1 trillion or some like comically large sum of money, right? Bet on the horse with the most favored odds. No kidding. Bet on the most likely winner. Got it. Thank you. Great algorithm. Okay. Don't gamble just don't gamble. Don't even do it responsibly. Okay. The only thing you should do responsibly is learn data science. Okay. Also, such a rule of thumb by itself is obviously very rough and inaccurate. It is not unreasonable to expect it to provide predictions that are at least slightly better than random guessing. Yes, if you predict the most likely winner every time, that is better than random. I claim that that is true, right? Okay. Furthermore, by repeatedly asking the expert's opinion on different outcomes and collections of races, the gambler is able to extract many rules of thumb. Now, this is getting interesting, right? Presumably out there is actually someone who has some intuitive understanding of the stock market that is better than everyone else's, right? That person exists at high probability. We can't necessarily figure out who that person is. Every once in a while, someone's like, it's Warren Buffett, and right? No, I think it's probably like a computer program running on a server in like Omaha, Nebraska inside their stat department, right? It's actually me. I'm secretly a billionaire. Okay, but I'm a billionaire in the way that matters, which is I have a wealth of students I've been able to teach, right? Okay, so there are in fact people that have intuitive senses for things, right? I have an algorithm that is difficult to articulate for deciding which slides to not show in my slideshows I teach in class, right? It's very difficult to articulate this, but I have a series of rule of thumbs. For example, as a rule, I don't show slides that have too much text on them, right? But I do have some counterexamples, right? This is a funny story, I left it in. This is an exact quote from the other two faculty that teach this class. I thought it was interesting, right? So if you interviewed me about course design, if you interviewed me about being a content creator for Instagram.com, right? All of these things, I have a series of rules of thumb I follow. Unfortunately, I got bitten by a radioactive computer scientist when I was 19, so I actually can write these down in Python, right? But normal people don't do this, right? You can go listen to content creators talk about how they manage their brand, and they have a bunch of heuristics that don't quite make sense, but are very close to being accurate, right? So my sense is this does in fact happen a lot of the time. There do exist experts whose rules of thumbs are very close to constituting some form of model, right? And please don't gamble, which means don't invest in the stock market. Okay, all right, that's okay. Okay. So how did I split this out? In order to use the rules of thumb to maximum advantage, there are two problems faced by the gambler. First, how do you choose what to ask the expert about? You have to make sure you're not asking about races that always have like an obvious winner, or that only occur when it rains, or that only occur when there's only a single horse, right? Because horses always beat humans if there's no humans running in the race, right? My model on a horse race is to predict the horse every time, and after a few years I found out that in fact there were no humans running against the horses at all, so I was 100% successful, right? Second, once you have collected many rules of thumb, how do you combine them into a single model? That's a good question, right? My entry-level categorization would be like, do a decision tree, because that's a good way to combine different questions, right? Boosting refers to the general and provably effective, citation needed, method of producing a very accurate prediction rule by combining rough and moderately inaccurate rules of thumb in a manner similar to that suggested above. Does this link work? Ooh, this one works. So, what year did this come out? 1999. What was going on in 1999? Well, that is right before the dot-com boom, right? So boosting is a slightly pre-big data mechanism that was developed. This is hosted at UCSD, right, even though it's owned by AT&T Bell Labs. Fun fact about AT&T Bell Labs, the people I know that were there were functional programmers, which means they wrote the same types of programs we write in R and not the types of programs we write in Python, right? So the people that came up with boosting are very much R-style programmers, right? I don't know that they were writing R in 1999. And they named their algorithm after Ada Lovelace, not after Alan Turing. So that's a callback to an earlier mentioned person. There are, in fact, formulas in this paper, so be aware of that. You can look at this or not as you're interested, but something that I think is very interesting going on. It's a long paper. A lot of the conferences I look at now have very short page limits. They're trying to keep us under 6 pages, and I think a lot of that has to go on. In 1999, there were many, many fewer papers being written, right? Data science academia is much larger than it used to be. I've spoken to this about a few of you. These fields are getting a lot bigger really fast, and it is very difficult for people to keep up with everything. So as you look at older papers, what you should expect is you should expect the best paper in a given year from 10 years ago to be a top 10% paper now, and you should expect it to be 4 times as long. This is very cool. It is exciting to be in a rapid growing field. These old ideas are very interesting and they're very insightful, and essentially every single researcher could come up with them now. We are so much more advanced at this method. Who is this? Was this like Amazon or something? No, this is just an example. Okay. So one way to think of this is we just have an iterative process where we throw data sets into training models. We test over and over again, and we save each of the models, and perhaps we modify the different data set each time. Perhaps we care more about different errors sometimes. Perhaps we just see new errors different times. And then when I think of these little knobs on here, right, I'm imagining taking a linear combination of these models, right? Like when I was in a band called Ghost Boat, we played local emo, right? We would always mix the bass and guitar really high because I was the drummer and I played way too loud, right? That was what I contribution to the band, right? So it always turned the drums way far down, and that's an example of a model that isn't very predictive, right? And then here's our bass player who is like pretty okay, and so that person has a higher setting. And then our lead guitarist was like absolutely epic and was carrying the entire band, right? So that person had a very high weight. But in fact, our lead guitarist wasn't very good at getting other bands to let us open for them, so we used the bass player for that, right? And then we used me for comic relief, right? So these are all the different ways that we can combine a different model, in the same way we combine different tracks on a soundboard, and this is the boosting operation. And once again, you can look at this here. Is this ever going to load? There it is. Ta-da, gradient boosting. And it's an R. XGBoost was confusing to use, so I didn't use it today. Okay. Time check. Okay, cool. XGBoost mentioned. Okay, so I try not to talk about computers too much. My impression. Caret seems to have a very specific internal mechanism for running many models quickly. The XG in XGBoost refer to another method for running a bunch of models very quickly. What this meant is I made the design decision this term to not teach XGBoost. XGBoost to me seems by far the most common boosting framework. It runs in every language. I got it to run in Python and R and JavaScript. I did not try to run it in Julia. I suspect it's possible. It seems to also run in CUDA C++, right? So XGBoost is very fast. It is language agnostic. And its language agnosticism is both a benefit and a cost. It means it is more difficult to teach it. It means it is more difficult to get it to work consistently with the same methodologies we've used in this class. So I'm going to show you a different boosting methodology. I want you to be aware of XGBoost, and I want you to know why not to use it in Caret. I think you are probably going to see code generated by generative AIs that suggest running XGBoost in Caret, because in fact it is quite likely that the method you use is XGBoost, and it is quite likely that the training model you use is Caret. You would just not use those things together because they have poor performance. They don't play well together. And essentially what's going on under the hood is both of them are deciding some way to divide up the multiple processors in your computer, and they fight. And you don't want them to fight. So I'm going to use a different method. I'm going to set a GBM grid, which is a generalized boosting models, which is not XGBoost, right? And I'm going to turn the settings for it way down. I think people use boosting for really big data sets on really big data centers with lots of computers. I have one little tiny computer. It's a little toasty, right? It's getting kind of warm over here, right? So I don't want to work it too hard. You can look up all the default options here, and I basically tried to turn this down so that there's a much smaller number of them. So there is only 2 possible values of trees. There is only 2 or 3 possible values of interaction depths, relatively small shrinkage, blah, blah, blah. I don't even remember what this stands. Minobi Synode. I used a generalized boosted model. I used the same control we used. That's k-fold cross-validation. I used the GBM grid, which is turning everything down as low as possible. And I just try and predict province. I get all these iterations combining different things. The training variance decreases pretty much monotonically over time, right? Each one of these keeps getting smaller. Yes, we take different steps. We can look at all of these. We take many, many iterations, right? This took a long time to run. I think several minutes for me. You can run it yourself and see what happens. And you can also go back here and just put only one number in these vectors, right? Many, many, many outputs, right? And then at the end, we have some very low variance, deviance, right? Low deviance. The deviance decreases across stages and also within iterations. So we have improvement every time. Okay, this is our GBM. Wait, here we go. Here's the confusion matrix. Pretty good kappa value. Not a kappa value that I think was worth the amount of time and tuning it spent to put into this. I think you would use boosting as a component of a broader machine learning flow where you get a pretty good model and then you boost across it, right? Or you would use XGBoost, which is dramatically higher performance, right? Take a look at XGBoost if you're interested. I don't think it's super necessary to use it just in the context of this class on assignments. Let's do one more. Random forest. XGBoost is pretty popular. It's around. My impression is I don't see R programmers use it a lot. It is definitely present in R. It is mostly not present in Caret. It might be used by like non-tidyverse R programmers, of which whom there's some number. I don't actually know. I really like to use like Google Trends and GitHub to take measurements of how popular different programming languages are, and it's impossible to look up how popular R is, right? Because I need R set minus tidyverse, and the problem with R is it's a letter, right? Very difficult to see how popular a letter is, right? So I don't know how much people are using XGBoost in R. I know they are. Anyways, they're definitely using Random Forest. Everyone's using Random Forest. I see Random Forest all over the time. When I go to the Portland R user group, they're all using Random Forest and KNN. Right? It's just Random Forest, KNN. That's the way we solve problems, right? Random Forest is not too complicated. Hopefully you've been tracking pretty well so far, and you've said, we took tree bag earlier. That was where we took a bunch of different trees, we gave them a bunch of different data, and then we evaluated how well each of them did, and we did some combination of them. Well, we can go one step further. In addition to giving them different subsets of the observations, which are the different rows, we can also take subsets of the columns. We don't have to give every tree all of the same entries in sort of the table, right? So we can take our Random Forest, and versus a tree bag, we might give one of the trees only Instagram and LiveJournal, and one of the trees only YouTube and LiveJournal. They don't all have to get every single measurement in every single observation. So that's basically the only difference between Random Forest and tree bag. And of all things, Random Forest works way better. Why should it work way better? Intuitively, we should have a sense that throwing out a bunch of features means this thing can be way faster, right? Every single step is cheaper and easier as soon as we start throwing out features, because features cost us money in terms of computation power every single time. Most of the features are probably useless if we have a lot of features, and if we don't have a lot of features, we're going to keep all of them anyway. Easy to imagine, we don't always want the same fixed number of features we happen to naively provide to the model. So this thing seems to work really, really well. It makes a little bit too much sense to me that you can always take a subset of observations and a subset of measurements and get a pretty good result. It is unlikely that every single one of the pieces of data you've collected is equally important, right? So we throw Random Forest into our model. Where is it? Pretty good kappas, right? 6.8, 6.7, 0.68, 0.67, 0.65, right? Our highest was still Lasso today, but these are extremely respectable. I wonder why that's scrolling off screen. Let's see what's going on here. I don't know. I don't know how computers work. Okay. I like these zeros. That's cool, right? Not a lot of misses in a lot of places, right? This isn't great. Marlboro is being projected in California and Oregon, as it always is, right? But it really looks like in our data set, Marlboro is just very similar to California and Oregon. There's our kappa value, 0.67. Our kappa values are getting up into that respectable range, right? Like everything we've done today has been over 0.6, and we can combine all of these different methods in different ways, right? This is sort of kind of the last thing I want to show you today. And then we're going to break up and you can talk to your groups. I wanted to compare tree bagging, which is trees that are bootstrap aggregated, with generalized boosting models, GBMs, with random forests, which is sort of tree bag in one direction, and then also this like feature selection in the other direction, right? Which is very similar to boosting. So random forest is sort of the perfect form of the decision tree that is adapted to both bagging and boosting, right? To do this, I am using the do parallel library in R. Why am I doing this? Well, I'm doing the same thing 3 times, and I can do all of those 3 things at once. My colleague that I speak with the most about R that doesn't go to this university says, I have never once in my life thought about how long it takes R code to run. because I simply submit it to a cluster somewhere else on campus, and it's done very quickly because that cluster has a large number of computers in it. I don't know the exact process my colleague uses to do that, but I think it is very, very close to this. I am doing something special here, which is that I am not telling R to run some code. I am telling R to schedule some code to be run. At some point, this must be done. And the benefit of doing that is it doesn't do things in order, right? All of these three models were fit at the same time. I put some effort into lining them up vertically, and we can scroll over here and see that most of the things I'm doing are the same. I did have to specify a tune grid here and max iterations. Only one of them is sort of shooting stuff out. I think that's GBM, right? And then I timed this whole thing. And look at this. User system elapsed. I did 52 seconds of machine learning in 8.14 seconds. Because I can do two things at the same time. I can do a random forest at the same time I can do a tree bag, because my computer has more than one processor in it. And if I'm working for the National Institute of Health, I have 1,000 processors, which means I can do 1,000 seconds of work every second. This is cool and good. One of the things that is really cool and good about this is you do not have to think about how fast your code runs. You only have to think about if it can run at the same time. That is a much easier problem to solve, right? Just earlier today, for example, I said, don't pick an alpha value, just try 20 of them. Yes, because you can do 20 alpha values in ElasticNet in the exact same time you can do one of them if your computer has 20 cores on it. I'm looking at a lot of computers here. I'm pretty sure all of them have 20 cores, right? Probably most of them have 32. Some of them don't. That means your boss needs to buy you a better computer, right? That's not my fault. It took me a minute to get this to work. I suspect this will not necessarily work by default on every device. I also spent some time at the beginning of class to talk a little bit about, like, hey, you should be fiddling around with your computer and making sure you can get all of these things to work, right? This fiddling around with of computers is one of the ways you can get the do parallel library to work, and I encourage you to do it. I have found, over the course of this class, a lot of what I have used to get pretty good at machine learning is being able to get code to run very, very quickly, so I can try a lot of things very fast and learn faster. So I'm not sitting around waiting for my computer to run. Do parallel is my favorite way to do that, and that's why it's the first one I'm showing you. The other way is like writing things in Python, which is like not super easy to learn. I am recommending you look into do parallel a lot. It is probably my favorite thing I've found in R so far. It comes with a paper. It's brand new. It's fast. This thing is cool, right? It's just cool. Oh, is there a word of caution? I can't read that because I've thrown caution into the wind. Okay. When I ran this, you only had to use 3 cores at a time to do this because I only have 3 things going. Right? But a very easy way to do this is library do parallel, git do power workers, just see if it's working on your device, right? And if it's not working on your device, panic. I am not in a position yet where I actually know how to help you get this to work, but I got the impression that it runs on Docker. Have you all seen Docker and Data 503? So I'm pretty sure what's happening is do parallel is creating our Docker images and throwing data into those Docker images, and then they're coming back. That's cool. You all know how to do that, right? Like you could write do parallel, and like maybe it's not as efficient as the people that published the paper on it, right? But there's no magic under the hood here, right? It's just Docker images. When you're done, stop the cluster. Presumably you have to do that. I don't know. I just followed the paper. It seemed to work fine. We bag, we boost, we random forest, which is also bagging and boosting and blah, blah, blah. And look at this. We can print out all the summaries. Oh, it's cool. I don't know. Accuracy, kappas. Look, the random forest kappas are way better than everyone else's. I don't know what's going on with my slides today. They look really cursed, right? But look at that, 0.69. That's our best fit today, random forest. Caught up with ElasticNet right there at the end. So that's cool. I don't know the best way to impress upon you the way that I would use this to come to conclusions about which machine learning algorithms I should use. This is how I solve problems. Run 5 or 6 things at once, look at all of their kappa values right next to each other, get a little bit, get like some post back from your computer how long it took things to run, know which ones are faster, see if it's worth getting an extra 0.01 kappa if it takes 2 minutes for the code to run, right? You have to make that decision, right? And with that, think critically. Don't just do things for no reason. But I am an expert horse gambler, and here are my rules. I always use weights. I use lasso unless it's easier to use elastic net. And I use random forest every single time. With that, talk to your modeling groups. Get your head on straight to have your models submitted by March 10th, which is next time. And I will walk around and talk to all of you as soon as I get back from getting a drink because my voice is going to explode. See you all shortly. I am going to turn this off right now because I am out of power.